Hello guys, let's start our second part of the Pushdown Automata. So far, whatever we said was about the deterministic PDAs. But yeah, you need to pay attention that all of those stuff that we have talked about are common between the non-deterministic and deterministic PDAs. Now, in this section, we want to focus on the non-deterministic PDAs. Let's start with the determinism definition to refresh your mind. You remember that we said during any time frame, there is no more than one transition. This is the definition of the determinism. So it means that there should be either zero transition or one. If there are more than one transition, it means that it will be a violation of the definition of determinism, and that makes the machine a non-deterministic. So now the question is how this definition will be violated. We have two different ways to violate this determinism. Either the lambda transition or having multi-function or multi-valued function. Okay, so let's start with the lambda transition. To refresh your mind, let's review what was the lambda transition. Lambda transition in any kind of automata, it means that machine can unconditionally transit. So it means that if we neutralize the condition for transition, the machine can transit unconditionally. How can we do that? Here is what we did in the DFAs and NFAs. So we put the input symbol as the lambda, but PDA now has two conditions for transition: input symbol and also the top of the stack. So we need to put lambda in both of them to make a lambda transition. What does it mean? Yeah, let's look at this example. So we have A and B. This guy is coming from the input symbol. This guy is the top of the stack. So both of them are conditioned for transition. We need to put lambda on both of them. So how? This way, right? But even though this is a lambda transition, but machine unconditionally can moves from Q2 to Q5, but it needs to do something, right? It needs to push this W. W is a string, whatever we put it here, right? Okay, so theoretically this is a lambda transition, but in practice really it makes the design more complex, right? And I will explain that we need to make it a little bit simpler. But before that, what is the lambda transition in NPDAs? Yeah, just putting lambda in the input and the pop part. So this is the lambda transition. Okay, so in practice, as I explained, we will be using this guy that is lambda in all of those three parts. And in this case, machine unconditionally moves from the Qi to Qj, and it doesn't need any, pushing as well. Okay, now let's talk about the multifunction example. So this is another way that we violate the determinism. Look at this. If the input is A and the top of the stack is B, move to Q2 and push W1. But wait a minute, we have another transition with exactly the same conditions, right? So this is one simple example that it's a violation of the determinism. So I ask this question, is this a violation? Yes, definitely it is. Because machine can move to Q2 and push W1 in the stack, and at the same time machine can goes to Q3 but push something else. right? So to handle this situation, definitely machine needs two processes, right? Definitely this is a violation of the determinism. I put together some other examples to show you that how different situation can happen. Look at this one. This guy is saying that if the input is A and the top of the stack is B, go this way. But this guy is a little bit different. It is saying that if the input is A, don't care about the top of the stack. So when machine encounters these two guys, then it has both of them satisfied, right? So machine can goes to Q5 and also at the same time machine can goes to Q6. So definitely this is another violation. We have more examples. Look at this one. In this way, we are saying that don't care about the input symbol. Just check the top of the stack. If it is B, move to Q8 and push W1. But this guy is saying the same thing, right? It is saying that if the top of the stack is B, yeah, exactly like this one, and if the input is A, right? If really the input is A on the tape, then machine can move to here and also machine can move here. So we have two possible transition at the same time. So definitely this is another violation of the determinism. And another example, here we are saying that this is actually a lambda transition. Machine unconditionally can move here and push W1 into the stack. But here we have the input symbol A and top of the stack is B. So in this case, I mean, if really the input symbol is A and if the top of the stack is B, then both of these transitions are possible. And this is another violation of the determinism. So it means that in some situation, all of these four are violation of the determinism. We have more situation. How about this one? This guy is saying that the input is A, top of the stack is B, but this is input A, but the top of the stack is C. So definitely it's not a violation. How about this one? This one is again not a violation because the input symbol is different. Yeah. With these examples, I want to show that both of these conditions should be the same somehow, right? In those cases, then definitely there will be a violation of determinism. How about this one? Don't care about the input. Top of the stack is B. Go to Q8. Yeah. Don't care about the input. Top of the stack is C. Yeah, definitely it's not a violation. How about this one? Yeah, this one is no violation. Yeah, you can go over that, but we still have more. Look at that. So here is it's saying that if the input is A, don't care about the top of the stack, go to Q2. How about this one? Don't care about the input, the top of the stack is B, then move to Q3. So if the input tape really is A, and if the top of the stack, let's say for example, yeah, if we put Z here, and let's say we are here, if the top of the stack is B, in this situation, definitely this transition will be a violation of the determinism. Yeah, I mean, in exactly this situation, machine goes to Q2 and at the same time it can goes to the Q3, right? So definitely this is a violation of determinism. We have more here. You can go ahead and try to understand why all of these are violation of the determinism. Now we are familiar with the lambda transition. Also, we are familiar with the multifunction or multi-valued functions. Now the question is how NPDAs behave if they have multiple choices. We already are familiar with a very general rule that if machine has several options, it start parallel processing. And this is the same rule which is valid for the NPDAs as well. So if you want to be very precise, then we would say, hey, if we have multiple choices, machine start creating new processes, and that creating new processes is exactly the same as NFA, right? I will explain that in a few minutes, but yeah, every process start, processing the string independently. Okay, now the question is how? Very simple, the same as the NFAs. Machine replicates its entire structure. Machine initialize the new processes with the current configuration, and each process independently continue processing the string. Okay, so the only thing that remains here that what is the configuration for the NPDAs? In fact, the configuration is common between the deterministic PDAs and non-deterministic PDAs. So the current state of the transition graph, the input string and the position of the cursor, and the stack and its content. So we don't need to talk about the stack pointer because it always points to the top of the stack. So these piece of the information are the configuration of the PDAs. Another question is how NPDAs accept or reject a string, right? We learned so far that one single process needs to have all of these conditions be satisfied. So halting, consuming all of the symbols, and halting in an accepting state, right? So this is only for one process. But how about if we have multiple processes? Yeah, the same rule as the NFAs. If at least one process accept a string, then that string will be accepted. And also for rejection, we need all of the processes reject that. It's time to turn to the mathematical definition. Let's start with the DPDAs first. A DPDA can be defined by a septuple or seven tuples. So Q, sigma, gamma, delta, Q0, capital Z, and capital F. What are they? So the Q and the sigma and the Q0 and F are exactly the same as the NFAs. So we are not going to talk about them. Let's just start with the new ones. The gamma is a finite and non-empty set of symbols called a stack alphabet. You remember I said that a stack alphabet can be totally different than the regular alphabet, the sigma. Yeah, so then we need to specify it with this separate set and we denote with the gamma. How about the delta? Yeah, definitely delta is always different. Okay, so how can we show them? This looks like a little bit, I don't know, complex, but it is really simple. So we need to union the alphabet with lambda, and also we need to union the gamma with the lambda, and then a Cartesian product between these three, and on the range side, we have Q, Cartesian product with the gamma star. What is this? I need to explain that in detail in the next slides. But for now, let's accept that whatever it is, right? The next question is this a partial or total function? So far, all of them were total function, but this one can be also partial function. All right. How about the z? Yeah, z is part of the gamma. So always gamma contains the capital Z because it's an alphabet of the stack on the bottom of the stack. And it is a special symbol that we call it stack start symbol. Okay, so yeah, just let's have a quick review. What is the Q and what is the sigma? What is the delta? What is the Q0 and F? And these two guys are the new guys, right? So the gamma is the stack alphabet and the Z is the special symbol for the stack that we call it stack start symbol. Okay, so now to explain that how that delta works, let's start with this simple example. Look at this. The question is, what is the subrule for this? Yeah, we are looking for the delta of what? So you remember, on the domain side, we had Q, Cartesian product with the sigma union with the lambda, Cartesian product with the gamma union with the lambda again. And on the range side, we had Q, Cartesian product with the gamma star. So what is this and how can we use that? So in the domain side, we have a three tuple. One is Q, which is the starting state of the transition. And then we have the input symbol coming from here. So it's coming from here and it will be A. And also we have the top of the stack. It's coming from here. So it is the delta of Q2 comma A comma X then equal to what? We need one Q and one string from the gamma star, right? So it means that go to Q5 and push whatever this is, YX, right? But since we don't have such thing in mathematics, we need to put it somewhere. So we create a two-tuple or order pair to show that what the range is. Okay, now let me ask this question. Why do we need this lambda? Because we can put lambda here, right? And since lambda is not part of the alphabet, we need to union that. How about this guy? The same thing. We can put lambda here as well, and lambda cannot be part of the gamma, right? So that's why we need to union that. All right, so this is the answer, and this is why we had to union the lambda with this guy and this guy. Okay, now the question is, how about delta of Q2 and B and X? What is the response for this? What is the value of the Q2 and A? Let's say because the gamma can be Y as well, Y here. And we can ask again, what is the Q2 with the B and Y here? So what are these values here? Yeah, we don't have any outgoing for all of these three. So actually none of these three. So it means that all of them will be undefined. That's why we said the delta can be partial function because we have some situation that they are undefined. So as you see, PDAs don't have the strictness of the DFAs. So there are some situations that there is no outgoing for some of the symbols of the alphabet. Another question, how can we write the delta here? So here, if we are in Q2, and if the input is lambda, as you see, this is one reason that we put lambda here, and we needed to add it to the alphabet. And if the top of the stack is X, then go to Q5 and push YX. Now, let me ask a very important question. Is this subrule equivalent to these two? So could we remove this, and instead of this one subrule, could we put these two? In other words, we consider this lambda as a wildcard, and we could say, okay, if it is A and the top of the stack is X, go to Q5 and push the YX. If input symbol is B and the top of the stack is X, then do the same thing. Could we replace these two guys with this one guy? You can pause the video and answer this question. Definitely not. They are not equivalent. Because if we replace these two with this one, it means that if A is the input symbol, then A should be consumed. The same thing for the B. But if we put lambda here, nothing will be consumed. So these two subrules are not equivalent to this one, because of the consumption stuff. Another example, yeah, this time we put lambda here on the top of the stack. Yeah, with the same reason, we can say that, yeah, the input is A and the stack don't care about the top of the stack, and the result will be Q5 and pushing this YX. Again, I want to ask this question, that can we replace these two guys with this one? For the same reason, they are not equivalent. Because if we put this guy and this guy instead of this, then we need to pop something, right? But here we don't touch the stack at all. Another example, yeah, I think your knowledge is enough for this one, and we don't need to talk more about this. The only difference is that we don't push anything. So, in other words, we notice that we can have lambda in any position here, and the reason that we union lambda with the sigma and gamma is now obvious. How about the other side? Yeah, I mean the pushing this. Yeah, we don't need to add any lambda over there, because if you remember, the range was Cartesian product between Q and the gamma star, and gamma star is exactly like the sigma star. You remember, if the gamma, for example, is equal to, let's say, x and y, then gamma star is equal to lambda, and then x and y, and xy. You remember that we had this sigma star, all possible strings that can be made by this xy, right? So as you see, lambda exists here, so we don't need to union the lambda here, right? And so forth. Now let's talk about the formal definition of the NPDAs. Uh, they can be defined exactly with the sept tuple that we talked for the DPDAs. Six of them are exactly the same, and we are not gonna talk about them. The only difference will be delta function or transition function that looks like this. So on the domain side, we have no difference, but on the range side, as you see, we are using the power set, right? And why we need to use the power set? The same reason that we talked on the NFAs. We have some situations that we have zero value or one value or multiple values. That's why we need to put them in a set, right? That's why we are using this power set, right? On the DPDA, we just had Q cross product with the gamma star. Now we are using the same set, but the power set for them. Okay, so for the same reason, it can be a total function. Now let me take some examples for this. Yeah, there is no difference with the DPDA. The only difference is that we would need to put the range inside a set. And there are some situations that we have empty sets like this. So since we have no subrule for the Q2, if the input is B, that's why the result or the range value will be empty. And we have the same thing for the other possible values. And as usual, we can eliminate all of those that are empty and just keep those subrules that has some values. Another example, here as you see the input is A, the top of the stack is X, and the same thing here. So in this case we will have two values for the range and we put both of them inside a set. In this section we are going to compare NPDAs and NFAs. So we want to know that which one is more powerful. How can we do that? We will be asking two questions. Whether or not can NPDAs simulate NFAs? Can NFAs simulate NPDAs? And the answer to these questions shows that which one is more powerful. Okay, let's start with the first question. Can NPDAs simulate NFAs? What does it mean really? It means that if we construct NFA for a language, so let's say this is a language and we have an NFA for that, right? Can we always construct a PDA for that? PDA, when I say it can be NPDA, it can be DPDA, right? Can we always do that? If we can do that, then it means that PDA can do whatever the NFA can do, right? So one way is to convert the definition of this NFA to PDA. If I can do that, then it means that in fact with a very simple algorithm I can convert the definition of NFA to a PDA. So in that case, yes, then we answer yes. Whatever NFA can do, PDAs can do as well. Okay. How can we convert the definition of NFAs to PDAs? Yeah, let's explain with this simple example. This is an NFA, definitely, and this is the definition. How can I convert this definition to an NPDA definition? That's a very good question here. So look at this delta on the left side and this one. If I just add a comma lambda to this one, and put this in an order pair and add a comma lambda here, it will be converted to this machine, will convert it to this machine, right? Can I do that? Yes. How come? Because I am saying that don't care about the top of the stack and don't push anything. So it means that I am trying to not touch the stack at all. For all of these transitions, if I do that, it means that I put aside the stack. And if I put aside the stack, what remains? Exactly an NFA, right? And this is how we convert the definition of the NFAs to PDAs, right? Okay, so let me summarize that. Is it possible or not? So should we change the states? No, the states is the same thing. The alphabet, no changes. A starting symbol for the NPDAs is Z, but this guy doesn't have. Of course, it doesn't have, right? I just need to add this, right? No more alphabet for the stack. Just the Z is enough. And it is always the constant thing. I can add this, right? How about the sub rules? Yeah, exactly. So just add a comma lambda here and a comma lambda here and put the range instead of this QJ, just put it in an order pair. No changes to Q0. Of course, it doesn't have the Z here. We just add it. Is a constant thing. And no changes to the accepting states set, right? So you agree that this is a algorithm that we can do on all of the NFAs and convert them to NPDAs. So if this is the case, I can do that always, right? I put all of those explanation here for your reference. So now we understand that yes, whatever the NFAs can do, NPDAs can do the same thing. All right? Okay, now let's ask the question the other way around. Can NFAs simulate NPDAs? If I have a language like L and I create an NPDA for that, can I always construct a machine that, construct an NFA machine to solve the same problem? Obviously, no, because at least I know one language that I couldn't do that for NFAs, but I could solve or recognize them with NPDA. So this is the answer and this is the reason, right? So it is really no way that we can simulate the stack operation with the NFAs. That doesn't have any writable memory at all. And these two are just counter examples that shows that NFAs cannot resolve or understand these languages, but NPDAs can do that. Now question is, what is the next step? Let's shine our knowledge and let's look at the machines and languages association one more time and see what we got so far. So we know that NFAs and DFAs just accept this portion of the languages that we call them regular language. And now we learn that PDAs can accept more than that portion that DFAs and NFAs can understand or recognize. Is there any other languages that we cannot understand with the PDAs? That's something that we need to find out. But before going further, this portion of the languages we learned that we call them regular language. This portion that can be recognized by the PDAs, we call them context free, right? Just keep this name in your mind, but we still don't know what it means. Yeah, we will get back to this context free later. All right. So if this is the case, then definitely PDAs are more powerful because we prove somehow that all of these languages here can be recognized by the PDAs. But at least there are some languages here that cannot be recognized by the DFAs and NFAs. And definitely PDAs are more powerful. Okay, now let's pause the video and try to create a PDA. It can be DPDA or NPDA for this language. Yeah, after some struggling, we find out that we cannot do that. And the same thing for the WW. This language cannot be recognized by PDAs. So what is the reason? Because the stack is not that much flexible. What does it mean? It means that, for example, if you are here, let's say you are here, and we have some stuff here, right? If you want to access this information, you need to pop all of this, and to reach here, it means that you will lose all of those data. So I want to say that a stack is not that much flexible for storing data and manipulating the data. Okay, so if this is the case, then we have some languages like this that cannot be accepted by the PDAs. So what is the next step? Absolutely, we need to introduce a new class of machines that can at least accept some more languages, more than the whatever that the PDA can accept. I put some interesting NPDA for you guys. So try to simulate this with the JFlap and try to answer this question. This can be a good exercise for you guys. And I put some other exercises here and also another exercise here. In this one, I ask you guys convert this NFA to NPDA. Also, we have an optional project if you would like. So since you are familiar with how we introduce a new machine, in this optional project, I ask you to introduce a new machine like the PDAs, but instead of the stack, you just put a queue. Okay, so pick a name for your machine and discuss what kind of languages it can be recognized and try to compare its power with the PDAs. I'm gonna stop here. See you guys in the next lecture.